you so much. Yeah, I also have a really long title, so I won't read out the whole title. But yeah, basically summarized as machine learning and Salmonella. So I'm so happy to be here in Australia. It's freezing in the UK right now, so it's really, really nice to be here. Also, my last conference before mat leave, so feels like a really good time to come and learn about what's happening in bioinformatics in Australia. Okay. Oh, so go forward with this. Yeah. All right, so I just want to say up front that this was my first grant that I got as a PI. And it was a really exciting grant to get. It was called a Springboard grant by the Academy of Medical Sciences in the UK. And it was really great because it enabled me to hire this really excellent postdoc called Dr. Sean Bayliss, who did the majority of the work on this project. I just want to acknowledge him up front. And also it was a great springboard for both me and him. So he's now gone into his first independent position at the University of Bristol. So it worked out really well for both of us. Okay, so we're in this kind of era of genomics big data, and I know you all know this. And it's so cheap. Ooh, okay. It's so cheap to sequence bacterial genomes in particular. So things like Salmonella, E. coli, that we have hundreds of thousands of the major pathogens, and it's now being used for epidemiology, public health, and surveillance. But we have so many genomes that we actually don't have enough of us, the bioinformaticians, to be able to process them. And that's because we're using it extensively in reference microbiology and public health surveillance. And we're using it for things like source attribution, lineage tracing, and outbreak management. I mean, everybody saw this during the COVID pandemic, that it was really useful for lineage tracing. But we need to actually understand how to do this kind of on a large scale and going forward. So we're actually now starting to think about ways that we can automate this and automate the classification of strains into epidemiologically meaningful classes, and to be able to use that for public health surveillance and pathogen management. And that's what I'm really motivated by. But how do we actually turn sequencing data into prediction models? So you know this if you've done any machine learning before, but let's just go over it so that we're all on the same page. So if you're trying to train a model, you need to give it a set of features to learn the associations from. And if we're thinking about genomic features, these could be SNPs, they can be k-mers, they can be unitigs. You can choose what you want to input. So you provide a set of features to the model to learn its association or signal from. And then you'll provide a set of observations, and these could be bacterial strains, viruses, it could be isolates, samples, with all their individual features. And what you get is basically like this, which will be a two-way matrix, and this can be really, really, really large. Oh, sorry, pressed the wrong button. Okay, and then also what you need to provide the model with is a set of labels so that it can learn what the metadata class or the phenotype that you're getting it to learn is. And this will go alongside all of your observations. Okay, so I'm interested in doing this for Salmonella. So Salmonella is a foodborne disease, and it infects around 78 million people globally each year, so it's of great public health concern. Foodborne Salmonella enterica causes diarrhea, fever, and abdominal cramps, and severe cases can cause hospitalization. So this is why we have public health management of this disease. We need to have epidemiological surveillance so that we know when there's cases happening, when there's outbreaks happening. And the UK has around 8,500 Salmonella cases annually, and this is monitored by the UK Health Security Agency, which used to be called Public Health England, but recently changed its name. And around 2,500 of them are serovar Enteritidis, which is the most abundant serovar that we get in the UK. And something that's interesting and relevant to the epidemiology of Enteritidis is that we have these global food trade networks that impact when people get Enteritidis. So Enteritidis is associated with the consumption of contaminated foodstuffs, particularly chicken eggs. So we know that it's usually associated with poultry products. But in the UK, we have national monitoring and vaccination programs, which means that we have greatly reduced our local salmonellosis incidence. But when you go into supermarkets in the UK, and I'm sure it's the same here, you'll find food from all over the world available to buy. And that's great because it's delicious, but it means that we're being exposed to potentially imported pathogens, and which means that we have this threat of foodborne disease. But also alongside that, foreign travel to destinations worldwide is also increasingly common amongst members of the public. So we're kind of returning to that pre-pandemic level of travel where people like to go on holiday. And that also means that they're being exposed to, again, food from other countries where they could be eating a foodborne pathogen. So the majority, because of all of those factors, the majority of enteritidis cases that happen in the UK are actually thought to be associated with either foreign travel or the consumption of imported foodstuffs. So in the epidemiology of enteritidis, we know that. And because of that, we're now starting to think about how we could have rapid geographical source attribution of enteritidis strains based on genome sequencing data to be able to have targeted epidemiological work to find the contaminating foodstuff. And I'm going to give you an example of why you might want to have rapid geographical source attribution, how that helps with your epidemiological investigations. Okay, so this is an example of geographical source attribution. This is a different pathogen, but it's another foodborne pathogen that's quite similar. So Shiga toxigenic E. coli. And so back in 2012 in Belfast, we had an outbreak of Shiga toxigenic E. coli that occurred, and there were more than 140 confirmed cases. So when we were investigating this outbreak, we found that 125 of the cases had gone to the same restaurant, and 15 cases were the result of secondary transmission. So we knew there was a problem with the restaurant. But then when we interviewed the patients, there was no common food type that had been consumed by all of the cases. So it's not like they'd all eaten the burger and we could implicate the burger as the contaminating food source. They'd all eaten different things. So we're kind of at a loss of, okay, well, we know the restaurant's the problem, but what in this restaurant is making people ill? So we did some sequencing of the outbreak strains. We looked at them phylogenetically. So we put them on a tree and we found that they clustered really closely with strains that had originated in the Middle East. So we then went back to the outbreak. Oh, keep pressing that button. We then went back to the outbreak control team and we talked to them and told them this genomic information, the genomic epidemiology of the outbreak. And they then went back to the restaurant and looked for foods that had come from that region. They found that there was some imported parsley from the Middle East. They then tested that and found that this was the contaminating vehicle and this was what was making people ill. It had been sprinkled on loads of dishes. So this is why you might want to do this, and this is why we're kind of motivated to use machine learning to do this. Okay, so if we want to be able to do geographical source attribution, we need the right kind of data to be able to predict it with a model. So since 2014, the UKHSA have used whole genome sequencing for all clinical isolates of Salmonella. So that means that they have a really large bank of Salmonella enteritidis genomes that we could use to train a model. So they were able to give us a data set of around 10,000 enteritidis genomes from a 5-year period, so from 2014 to 2019. So this means that you can make your really large two-way matrix where you've got all the features and then 10,000 columns. But we need the labels as well. So luckily for us, there's also some epidemiological work that happens at UKHSA. So epidemiologists will perform enhanced surveillance phone calls that record whether a patient has recently traveled to a foreign country. So we had this data for about 34% of the isolates. So about 3,434 isolates also had a label which told us where that person was likely to have got their infection from. Okay, so that was the data set, but we knew that there was also a source of potential bias in the data, and that was the overrepresentation of clonally related outbreaks. So we didn't want to build a model that was trained to just predict a whole load of outbreaks. We wanted it to be kind of representative of the global population, so we wanted to downsample those outbreaks. So we took a single random representative isolate per country for each clone, and this was defined as a 5-SNP cluster. So after we'd done some quality filtering, downsampling of the outbreaks, and removal of the low incidence countries that were represented by less than 10 isolates, we had 2,313 genomes from 38 countries and 4 continents that we could include in the model. And before you dive straight into, here's my problem, I think machine learning will be the good solution for it, you really need to ask yourself if you think that this data set is suitable for machine learning. And I think you have to have a really clear signal for a machine learning model to pick up. And we were quite confident that this would be a good data set for machine learning for 3 reasons. So the first is that it had a really strong phylogeographic signal. So if you draw a tree of those 2,000 Enteritidis genomes, you'll see that cases where the patient has traveled to the same region of the world cluster together. So that's that phylogeographic signal that you can see on the tree. On that side as well. So we knew that kind of tells you that all the information that you need for those predictions should be in the genomes. We also had good worldwide sampling, so we'd sampled 38 countries in the world. And we also had a consistent temporal signal. So over the 5-year period, we were sampling all regions of the world every year. Okay, but we did see that there were some regions which were much more heavily represented than others. So in our data set, there were a lot of representatives from Asia and also from Africa. There was absolutely none from Australia. So that's probably because we don't have a lot of people traveling to Australia. It's a long way, and very, very few of them are coming back with an enteritidis infection. But we looked at which countries were most likely for people to be going to them and coming back with an enteritidis infection, and we kind of calculated that as the class proportion of all classes of the proportion of travelers to that country of all travelers. So basically, this told us that places like Egypt and Turkey, of the total number of people who travel there every year from the UK, quite a large proportion of them get enteritidis. Whereas places like Spain, where there's a really, really large number of people who go there, even though a lot of people come back with enteritidis, it's still a small proportion of the total number who go to those countries. So we knew there was different risk for different countries. But we also wanted to check that it really was the right data set to build this model. And we knew that there was a whole load of enteritidis genomes on NCBI. So we thought, is it better to just use what's available on NCBI and try and build a model from that rather than this public health surveillance data set that's just come from the UK? But we actually found that there was more uniform sampling in the UK data set than there is on NCBI. And what's been uploaded to NCBI is kind of sporadic. There's certain countries that aren't represented at all on NCBI, but are in the foreign travel data. And quite often it's just outbreaks that have been uploaded to NCBI. So we went forward with the UKHSA data set. So we were pretty happy that we had a rich data set, and this is what we aimed to do with it. So the first thing was we wanted to build a model that could run as fast as possible because we wanted it to be useful in an outbreak situation. So we wanted to be able to go from sequencing to answer as quickly as possible. So we designed it so that it worked directly from FASTQ files. And we wanted it to go directly from these reads, meaning we can eliminate assembly time and we can hopefully eliminate assembly errors. So what we did was we converted our FASTQ files into unitigs. These were the features that we were using for our model. And then we wanted to have a detailed classification. So we wanted to output a granular prediction for epidemiologists to interpret. And this is that hierarchy that I'm talking about. So we built a hierarchical model that could predict the region, sub-region, and individual country and provide levels of confidence at each stage. So I'll talk about that a bit more on the next slide. And then we employed a fairly standard machine learning approach where you split your data into 75% train, 25% test. You build your model on the training data set, and then you classify on the test data set to see how well the model's doing. But then the other thing that we did was we validated the model. It's really important to do this because just because you've built a model that works really well on your training data set doesn't mean that it's actually a good model for external data sets. So we wanted to build something that could be used potentially by other countries, other public health bodies, and we needed to validate it to be able to do that. Okay, so that hierarchy that I talked about. So obviously, when you think about geography, it follows quite a logical hierarchy in terms of you can go from much bigger aggregated geographical regions down to smaller subregions and then individual countries. And we wanted to build something that could predict at all those levels. And basically what this is it's not just one model, it's a series of models. And when you have your sample, it goes through these, like this decision tree of different models. And a multi-class classifier is trained per node of that tree. And this is what the output looks like. So it generates a separate probability score per level of the hierarchy. So you could say, for example, we've got 90% confidence that this is from Europe, and 70% confidence that it's from Southern Europe, and then a little bit less confidence that it's from Spain. And this is to provide that granular prediction to the epidemiologist to interpret, and for them to use multiple layers of evidence for their investigation. But the other thing we wanted to do was not force a sample into a class that we didn't have a lot of evidence for. So if a sample if we didn't have anything in it like it in our training data set, we couldn't match it phylogeographically, we didn't want to force it into a class. So basically we said, if a probability score of less than 0.5 is assigned at a node, then the sample does not proceed deeper into the hierarchy, and we don't try and force it into a class. Okay, so we used a classifier model, so we used a random forest. We rebalanced our data because it was slightly imbalanced. We're using a random oversampler, and we used feature selection and used the top 25,000 features in the model. This is what the model looks like. I'll just take a quick sip of water. If you have a look at the model. So it's colored by accuracy scores, the F1 scores, and green is good, red is bad, as you'd expect. Okay, so what you'll notice is, I've covered it up with the figure. But basically, we were really happy at that top level of the hierarchy when we're dividing between the 4 regions in the model. It's performing really, really well. We get very good accuracy scores for the test data set at the regional level. But then, as you'll notice, as you get down to the country level, there's some countries that are performing really badly that are in red. And those are the United States, France, and Italy. And we were interested in why these weren't doing so well, but we also noticed that there were some countries which were being predicted really, really well. So those were Cuba, Egypt, Indonesia, Jamaica, Malta, Spain, Thailand, Tunisia, and Turkey. And these had really high accuracy in the model. So we looked into why those countries were doing badly, and I think it's quite intuitive that the variation in classification and accuracy was negatively associated with both low sample number and increasing within-class genetic diversity. So there was a clear correlation between number of available samples and classification accuracy. So those ones that had done badly, there just wasn't a lot of examples in the model. It's not many people going to those countries and coming back with an enteritidis infection. And then the genomic diversity was estimated as the number of 25 SNP single linkage clusters divided by the total number of samples per class. And 2 of the most poorly classified classes, so France and the United States, had both low sample numbers and very high genetic diversity. So this tells us that what the model is seeing for that class is very few examples, and those examples are really different from each other. So there's no clear signal for the model to learn for those countries. Whereas the countries that have done really well, so Cuba, Egypt, Turkey, etc., are down here at the other end of the scale on the genetic diversity. So they have particular lineages that are very closely associated with those countries, probably endemic to the chicken population there. And that's a very easy signal for the model to learn. That lineage is associated with that country. This is what the model looks like, the results of the model, if you put it on the tree. So you'll see, as I mentioned, that at the regional level, it's doing really well. Sub-region pretty well, but then when it gets down to the country level, there's certain areas of the tree, like this clade in particular, that isn't predicted well. But I think what's quite encouraging is that we have these p-values that tell you how confident the model is in its predictions. And it's getting it wrong this whole time, but it's got very low p-values at that particular area of the tree. So it knows it can't predict that part of the tree very well. Okay, so then we were on to our validation. So we built a model that worked really well for certain countries, but we needed to validate it to see whether it actually could be useful for outbreaks. So there was 2 ways that we could validate it. And the first was to look at some outbreaks where they had been epidemiologically traced, where it was an imported food outbreak that happened in the UK, and we'd epidemiologically traced it, so we knew exactly where the outbreak had come from. And we could run it through the model and see if the model got the same answer. So in 2015,